Okay, so our next speaker is Thomas Vandermeulen from SUNY Albany, and he will talk about resolving anomalous orbifolds. Please take it away.
Okay, thank you. I'm going to talk today about basically about what to do when you want to take an orbifold, but you may have a gauge anomaly. And this is based on some work that I did with my advisor, Daniel Robbins, and Eric Sharp. And to start out, we're going to talk about sort of how to take a constructive approach to orbifolds. And what I mean by that is we want to be sort of minimalist here when trying to build an orbifold partition function. And in particular, we're not going to make any assumptions off the bat about the form or the existence of any twisted Hilbert spaces that we might have. So we're just going to start with our parent theory partition function. So that's what we'll call the original theory. And of course, you know, we expect to be able to write the partition function as some sum over states. And in order to start building the orbifold partition function, of course, it's quite familiar that what we're going to do is we're going to insert some representation of our group. So here I'm denoting that by rho of G, acting on those states. And, you know, we insert that into the sum over states. And that gives us these objects, the Z1G here, which I'm calling partial traces. That's the name that we've been favoring for them. Sometimes people call them twisted sectors or twisted partition functions. But of course, you know, summing over the second index G here gives you the trace over the H twisted Hilbert space in general, so hence partial traces. And you know, these objects that we build, that the orbifold partition function is made out of, we know that they're not independent of each other, right? We can sort of build an original set here by inserting the action on the parent theory partition function. And then we can use modular transformations to start building the other partial traces in our theory. And just by considering the action of SL2Z on the torus, we can create, you know, we can get to the various partial traces in our theory. So let's take a look at sort of the simplest example, which would be a cyclic group, Zn. And let's make a very particular choice of SL2Z element here. And the reason I'm doing this is this formula that I have here, where now I'm indexing these partial traces with integers, since we're just talking about cyclic groups. It turns out that in this case, we can get whatever partial trace we want, these, you know, arbitrary ZMNs, simply by making modular transformations from the untwisted sector, from the original partial traces. And this is, of course, nice because, like I said, the untwisted sector partial traces, those are the ones that we actually know how to build, right? We know that, you know, it's just inserting the group, you know, acting on the states of our original theory. And the expectation here is that if we do something like this, then these indexes, this M and N, should be N periodic if our group is Zn. And also, a construction like this is going to fix all of the coefficients in front of these partial traces. And what I mean by that is, of course, we have this condition that the vacuum state in the orbifold should have unit normalization, right? And so this means that the this fixes the coefficient in front of the untwisted sector partial traces, because we're going to normalize by 1 over the order of the group, which in this case is n. And because the other twisted partial traces are obtained simply by making modular transformations, that's going to fix their coefficients too. So for a concrete example of what I'm talking about, let's just take our group to be Z2. And we know that if we're calculating the partition function for a Z2 orbifold, then there's going to be 4 different possible partial traces, and they come in 2 orbits. So here I'm using angle brackets to denote the sum over elements in an orbit. And this will be a useful shorthand, because of course the action of the modular group is just going to be to permute things within an orbit, right? So the parent theory partition function, the one that we started with, which in this case is Z00, that always forms its own orbit because, by assumption, the theory we started with was modular invariant. So the modular group won't do anything to that partial trace. But to the other ones, the modular group is just going to swap these other 3, the 0, 1, the 1, 0, and the 1, 1. And then, of course, the Z2 orbifold partition function is just the sum of these 2 orbits, which are, again, by themselves, modular invariant objects. But like I was saying, because we know that the vacuum in the orbifold theory has to be unit normalized, and we have this 1/2 out front, that fixes the coefficient in front of the Z01 term, and then modular transformations fix the coefficients, for the entire orbit. So that's the partition function. There's no unfixed coefficients, no choices to make. But of course, the procedure I'm describing, you could immediately object to. You could say, okay, well, that's all well and good for cyclic groups where we can obtain everything from the untwisted sector, but that's not the general story. And you would be correct that it's not always the case that all of the orbits include, a partial trace that is in the untwisted sector. So a counterexample, of course, is Z2 cross Z2. And in this case, there are 5 orbits, and one of them, which I'll denote by ZAB, has no untwisted sector elements. And so its partition function has this orbit where a priori nothing about genus 1 modular invariance is going to fix the coefficient in front of that orbit. But the procedure that I'm describing can be extended to higher genus. So we can, in this example, go to genus 2, and there's still the notion of an untwisted sector. Now I'm stretching things a little here because at genus 2, we don't have the notion of the partition function as a sum over states. So while there is still sort of a notion of an untwisted sector, we can't quite describe it in the same way. But morally speaking, we still have these untwisted sector partial traces. And so in the Z2 cross Z2 example, we can do the same thing that we did at genus 1. We can sort of repeat the procedure where we start with the untwisted sector, we take modular orbits, and we find that, again, most of the orbits are connected to the untwisted sector. And in this case, again, one of them is disconnected. But now, because we can relate the genus 1 and genus 2 partition functions by degeneration, matching up the coefficients when we degenerate genus 2 down to genus 1 is actually going to end up fixing this previously undetermined coefficient in the genus 1 partition function. and we're going to learn that it has to square to 1. And of course, this whole thing is a feature rather than a bug, because we wouldn't have wanted the entire partition function to be fixed at genus 1 without choice, because we know that Z2 cross Z2 is a group that has discrete torsion, right? And so another way of looking at that discrete torsion is sort of the presence of disconnected modular orbits. But we've learned that we can at least derive the fact that, you know, this discrete torsion should be given by Z2 just by looking at genus 2. So in principle, everything works out if you include higher genera. So returning to the cyclic orbifold example, where we can sort of work out everything fully. The general partition function is going to have this form based on those modular transformations that I wrote earlier. So, you know, we can use modular transformations to write everything in terms of the untwisted sector partial traces. So what we're doing is we're building this orbifold partition function from things that we can explicitly calculate, just, you know, write things as a sum over states, insert group elements that are acting, and then make modular transformations. And this all is well and good and works fine when the symmetry is not anomalous. But now the issue is that the symmetry might have an anomaly. And in that case, so I mentioned earlier that, you know, we expect that the indices on these objects are going to be n periodic. A gauge anomaly in one of these cyclic symmetries would basically show up as a failure of these indices to be periodic. And so the question is, this method of, you know, constructing the orbifold partition function, can we make it work? Can we preserve modular invariance even if we have an anomaly? And so some work that I did with Daniel a few years ago, we based things on the observation that, well, if we have an anomaly, okay, we know that the anomaly in a G symmetry is classified by the third group cohomology, H3GU1. And we know that if our group were Z, the infinite cyclic group, well, H3ZU1 is trivial. And so that means that a Z symmetry can't have any gauge anomalies. So in this case, what happens if we just take our finite cyclic group symmetry, our Zn, and just say, no, it's not a Zn, it's a Z symmetry. It's just an infinite cyclic symmetry, but one that's very redundant, of course. So what happens if we take the same thing that we had before, but now we take this M and N that we had, and we just sum them over all integers. And well, what we get is still modular invariant. In fact, again, if there's no anomaly, this should essentially be infinite copies of what we had before. But of course, you could object to, you know, I'm writing 1 over mod Z out front, and well, that's infinite. And the sum is infinite as well. And so maybe we have to, you know, be very careful about how we're regularizing things here. But it turns out that we can do something similar, but keep things finite. We can actually achieve the same result by only taking our indices up to n squared instead of n. So this, the fact that this works is less obvious. But in fact, even if the symmetry is anomalous, it will suffice to take things up to n squared like this. And of course, again, if the symmetry is not anomalous, this would be the orbifold partition function because it would be n copies of it, and then one of the factors of n out front would cancel, and you would just have the usual orbifold partition function. And by construction, this thing that we get here is modular invariant. And again, this works out, this gives you something sensible, whether the action is symmetric or asymmetric, and in particular with asymmetric actions, they may be anomalous. We know many examples of that, of course. But this object that you build is always modular invariant and always gives you a sensible partition function. The trick, though, is that you know, when there is an anomaly, that there's going to be cancellation because of the anomalous phases that show up. And you might just end up back with the partition function you started with. Or you might end up with an orbifold by, say, a subgroup of your orbifold group. And that's sort of interesting. So this is something that we observed and in doing this work, and we wanted to sort of contextualize this and figure out, okay, what's going on in general here. So so we can sort of rephrase things in a slightly more formal way. Basically, what we were doing here is we were taking a cyclic Zn symmetry, and we were extending it to a Zn squared symmetry. And you know, for any group G, the general version of this is we would take some symmetry G. We would know what its anomaly is, so it's specified by some class in H3GU1. And what we would want to do is find some extension of G such that the anomaly pulls back to something trivial in H3 gamma U1. And once we do this, the question is then, okay, what is the, you know, what form does the orbifold by gamma take? Which, you know, on the face, this might sound like kind of a ridiculous proposal because I've said, okay, start with a symmetry G, which is anomalous. So it has a gauge anomaly. We know that we can't consistently orbifold by G. So I'm saying, okay, instead, we're just going to sort of pretend our G symmetry is in fact a gamma symmetry, some other different group, which isn't anomalous. And then we're going to orbifold by gamma, which, you know, might sound like, okay, how can you actually do that? But what we know is that if we're going to be able to do this in general, if we're going to be able to always pick, you know, some k by which we can extend G to a different symmetry, that k is not necessarily something that acts effectively on the parent theory. It's basically a you know, a formal device, a bookkeeping device. So k is some group that has trivial action on the parent theory, which means that the orbifold by gamma has a subgroup, namely k, that acts trivially on the theory. And we know that when we have an orbifold by a group with trivially acting subgroups, that orbifold is going to decompose into a direct sum of other orbifolds. This comes from excuse me, my microphone cut out. This comes from work that Eric had done and has been working on for a long time. And in fact, the sort of, resolution to the puzzle in this case is going to be that, well, what is the form of the gamma orbifold? It does decompose into orbifold, into, a direct sum of other orbifolds. And those, the constituent orbifolds are going to be orbifolds by non-anomalous subgroups of G, which of course, that's sort of what it had to be all along, right? Because if we're going to form an actual consistent orbifold, then the only consistent symmetries that were available to us to start with were the subgroups of G that were non-anomalous. And so by extending our symmetry from G to some larger gamma, we're in fact in some way encoding a choice of subgroups of G that the gamma orbifold decomposes into, a choice of non-anomalous subgroups of G. And one thing we realized in doing this work is that when you have an orbifold with a trivially acting subgroup, there is in fact a choice that you get to make, sort of like discrete torsion. It basically tells you what the action of K is in the twisted sectors, because I said that K acts trivially on the parent theory, but it turns out that K can have non-trivial action in the twisted sectors. And the choice of that action is, in this case, going to be classified by H1G, H1KU1. And that's going to basically give you certain modular invariant phases that you insert into your partition function. Again, just like with discrete torsion, but this is, these phases are unique to orbifolds with trivially acting subgroups. So that was
about 5 more minutes.
Okay, thank you. So that was a fun little thing to run across there. And we've also done some work sort of classifying how these phases work in a general setting, not necessarily related to anomaly resolution. And so to close out, let me just give some examples of how this sort of general story works out. So for instance, let's again return to a Z2 cross Z2 symmetry. Let's say that, this was our original symmetry. The possible anomalies that this thing could have are classified by Z2 cubed. And basically what it turns out to be is that, this group, of course, has 3 Z2 subgroups, and any combination of those 3 could be anomalous or not. And so, what is anomalous and is not, we're gonna classify by these epsilons here. And for example, we might have the B and C subgroups being anomalous, but the A subgroup non-anomalous. And the way that these anomalies show up in the partial traces are like so. So of course, if the Z2 cross Z2 had no anomaly, all of these would be invariant under tau to tau plus 2, but we might instead get a phase under this modular transformation. And so if 2 of the subgroups are anomalous, then that's like one of the Z2 factors being anomalous and the other one not being. And so we basically extend one of the Z2s to a Z4 in order to cure that. Another example is just one Z2 subgroup might be anomalous, in which case, in order to resolve the anomaly, we have to do a less trivial extension to D8, the order 8 dihedral group. And then when we do the orbifold by D8, it decomposes into either the Z2 subgroup generated by A or by B. Again, both of which are non-anomalous. And the nice thing is that the D8 orbifold has a Z2 choice of discrete torsion, and that choice of discrete torsion simply swaps us between the two non-anomalous Z2 subgroups. Or one final example, all three of our Z2 subgroups could be anomalous, in which case we find that the, sort of the smallest thing that we can extend to resolve things is the non-trivial semi-direct product of Z4 with Z4. And when we orbifold by that, we simply get the parent theory back because there were no non-anomalous subgroups other than the trivial one. So of course, there was no possible orbifold that we could have done. So to wrap up, we're working on extending this story to 3D possibly. 3D gauge theories are known not to exhibit decomposition, so there won't quite be the same story. But the question is, how does anomaly resolution work in 3D? And that's something we're thinking about. And also in 2D, can we sort of generalize this to maybe non-invertible symmetries as well? There's sort of a whole story of using fusion categories to replace groups, and how does our work fit into that story? That's another thing we're thinking about. So thank you.
All right, thank you, Thomas, for this interesting talk. Questions? Yes, Craig.
Hi, yes, I had a question. So I just wanted to make sure that I understand. So at some point you had a sum over basically of M and N over Z.
Yeah.
And if you add this, you cancel the anomaly, and then you said that you can reduce this down to just over up to N squared.
Yes.
Am I understanding correctly? So the reason for that is that in the short exact sequence that you wrote down,
yes,
the Zn squared is essentially the smallest extension of Zn.
Yeah, it's exactly, that's it's basically the smallest extension where we can guarantee that the class in the given class in H3 Zn U1 will pull back to something trivial in this case H3 Zn squared U1. Basically, if the anomaly has order k in Zn, then the smallest extension that we can build that trivializes that is a ZKN.
I see. Okay.
And of course, k always divides n. So in general, n squared is going to be the smallest thing that will always work.
I see. Okay, good. And then I wanted to ask, so this seems to work if you're picking like an abelian subgroup of Z squared. So what if you have a gamma which is non-abelian, which extends Zn? Do those situations occur, and how does that?
Okay, yeah. So if you extend Zn to something non-abelian, I mean, because for instance, this example here, in this example, gamma is non-abelian. Sometimes gamma will be non-abelian, and it basically works out the same way. There are some interesting subtleties regarding decomposition with non-abelian groups, but modulo those, yeah, there's nothing too special about it being abelian or non-abelian.
But I guess in the non-abelian case, you can't write it as like a special case of the sum over M and N.
That's right. So for cyclic groups, we can always take a cyclic extension to resolve the anomaly. Right. Yeah, we probably could take a non-cyclic one and still resolve it. But I guess you don't have to. So why would you? But you absolutely could. Yeah.
I see. Okay. Very good. Thank you.
Okay. Yes, and